Okay, this is MA 161, exam 2 from this one is spring 2022. So this is the second to latest exam for these exam 2s. So there you go. Starting with question 1, this is just a limit as x approaches infinity of this big fraction. So something that I'd like to try to start off is since the numerator, or sorry, since the denominator has these two fraction terms here, it would be really cool if we could rewrite the numerator in a form where it's also two parentheses being multiplied, and one of them is one of these two terms there, so they cancel out. Usually, when that happens, your resulting output will be in a form where if you plug in infinity, it'll all check out and you'll get your answer. But I don't think we can do that. 1 minus 2x squared doesn't lend itself to any factorization that you learned in like algebra and stuff. So at least I can't see any that we can do right off the bat. So instead, what I think we can do is L'Hopital's rule. So if you were to plug in infinity for these x's, looks like on the numerator we would get 1 minus 2 times infinity squared. That's just going to be 1 minus infinity, which is negative infinity. And on the bottom, we're going to have 2 minus infinity, which is negative infinity, times 2 plus infinity, which is positive infinity. And that basically also equates to negative infinity. So we're going to get infinity over infinity because the minus signs cancel out. And this is an indeterminate form. An indeterminate form is either infinity over infinity or 0 over 0. So since we have an indeterminate form, we can use L'Hopital's rule. And L'Hopital's rule is just you can take the derivative of both the top and the bottom, and the limit will stay the same. So usually when you do this derivative, you'll get some sort of function that doesn't have any x's in it, and then that'll be your answer. So let's take the derivative of both the top and the bottom now. On the top, we're going to have, all right, derivative of 1 is just 0. Derivative of constants is always 0. And then derivative of 2x squared, we're going to take the 2, bring it out front. So this is going to be 2 times 2, which is 4, negative 4x to the power of, so this 2 minus 1 is 1. So negative 4x. Now on the bottom, looks like we'll have to do the product rule since we have two terms being multiplied here. And the product rule, once again, if you have something in the form of a times b, the derivative of that is a prime b plus ab prime. In our case, a is 2 minus x and b is 2 plus x. So substituting those in for a and b, we get, so a prime is the derivative of 2 minus x, which is negative 1, since derivative of 2 is 0, derivative of negative x is negative 1. Then it's just b, 2 plus x. I'm going to save myself some room here. This was negative 1, 2 plus x, plus a, which is 2 minus x, times b prime, which is the derivative of 2 plus x. So the derivative of 2 is 0, derivative of x is 1. So there we go. We have our derivative now. Now, let's see. Maybe we can multiply these out and see what we get afterwards. This will become, so still 4x on the top. This will be negative 2 minus x plus 2 minus x. Looks like a lot of these are going to cancel out, actually, like these two 2's. And these 2 minus x's are going to become negative 4x over negative 2x. The x's are going to cancel out, and we're left with just 2. So that is our answer. So by doing L'Hopital's rule here, we managed to get our original limit in a form where it no longer had any x's in it. And because of that, it just left us with our answer. Isn't that cool? Question 2, this is another limit where x approaches negative infinity of this big fraction here. So I'm going to take this question to teach you guys about how you can use kind of like approximation techniques to figure out a lot of these limits as x approaches infinity. So in these situations with this infinity here, you get some flexibility in how you can structure and rearrange the function to suit your needs, and that makes it a lot easier to find out what this limit is without actually going through a full gamut of calculus. So what I mean by that is, since infinity is such a big number, things like +5 and +1, they don't really do a whole lot in the grand scheme of things. Like that really just moves it, up 5 or down 1 or whatever it is, and that doesn't really change what a limit as x approaches infinity is. So for the sake of this problem, we can kind of just ignore those. Like imagine this +1 and this +5 aren't here. So now this problem becomes the square root of 16x squared all over x. And this is pretty easy to simplify now. This top can, this square root, that simplifies down to 4x all over x, which equals 4. Now, the answer might be A, it might be 4, but before we go ahead and lock that in, sometimes these approximation techniques can make like subtle changes in your output. Usually it's like a sign being flipped. So to check if we've got the right sign, if it's positive or negative 4, we can just go ahead and plug in like a really large negative number into our original equation. Like we can go ahead and plug in, say, -1,000. That's a pretty easy number to plug into functions. We can go ahead and plug it into this and see the sign of the output here. So if we were to plug in a negative number, let's see, this 16x squared, if we plug in a negative in there, it's going to become positive because of the square there. And this is a +1, and this is a square root, so this numerator is going to stay positive. And then if we do the same on the bottom, this x is going to be negative, and this +5 ain't going to change that since it's such a big negative number. So the numerator is going to be negative. And a positive over a negative equals a negative. So our answer is actually -4 instead of +4 like we were led to believe by doing our approximation. And that is actually the right answer. If you're going to plug this into like Desmos or Wolfram Alpha or something, you'll get that x approaches, or the limit as x approaches negative infinity is -4 for this problem. So that's pretty telling. Like you can really only use these techniques on these infinity limits, unfortunately, when x approaches positive or negative infinity, because just due to the nature of how the curve goes as it approaches bigger and bigger numbers, you can sort of rule out things like I showed you with the +5 and the +1. So unfortunately, it really only applies to these, but there's still a pretty common question that they like to give you on these exam 2s. So it's still worth knowing how to do these. Question 3, we have a derivative question. So we have f of x equals e of x. Not a terribly complicated function there. We have to find f's derivative and then plug in e. Oh, except we don't. It wants us to find it using the limit definition of the derivative, the thing where f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. That big thing that you learned like a month ago. So, all right, so it's just a matter of plugging in e of x, or e to the x for f of x, and then all those values in there we substitute as well. And it doesn't even look like we have to simplify it. We kind of just plug in the values, and then that'll be our answer. So that's cool. Probably won't be too much work. So doing all this, we get limit of h approaches 0 of, so f of x plus h is e to the x plus h minus e to the x, that x there, all over h. And then we just have to plug in e for x now. So this is now limit as h approaches 0 of e to the e plus h minus e to the e all over h. Wow, we already done. Answer choice E. There we go. Question 4, a piecewise function. So g of x is defined as 5x minus 13 whenever x is less than 2. It's defined as -5 for when x equals 2. And it's defined as x minus 5 for whenever x is greater than 2. So knowing all that, The g of x is not continuous at x equals 2 because what? What reason is it for not being continuous at x equals 2? All right, let's go through each of these one by one. I think that's our best bet. So, A, g of 2 is not defined. Well, yes, so that one can't be right because it is defined at x equals 2. It's this. When you plug in 2, it'll use that definition there, and the output is -5. So we know that one can't be true. What about B? The limit as x approaches 2 of g of x does not exist. I think that one is true, actually. So let's see. If we were to plug in 2 for this definition and this definition, will we get 5? I know that these definitions are between when x is less than or greater than 2, not equals 2, but we still need these two definitions to approach the same value if we want the limit to exist. So if we were to plug in 2 for the first definition, we get 5 times 2 minus 13, which equals 10 minus 13, which is -3. Uh-oh, that's a problem. This -3 is different than -5, so I think this is going to be our right answer, but let's verify it. If we were to plug in 2 for the second one, we get 2 minus 5 equals -3 as well. Okay, so that's probably our culprit there. Both the first and the third definitions of g of x approach -3 when x equals 2, but the middle definition there, when x equals 2, it equals -5 instead. So what this is going to look like is, so these are both just, lines, they're linear functions. So this is going to be like that, just a normal line, and then it's going to spike down to -5 there, and then go back up for that one. Like if this was 1, 2, 3, it would be like 1, 2, 3 for all those definitions. And since we're asked to find the limit as x approaches 2 right there, it doesn't wait. No, I've been mistaken this whole time. The limit does exist because both the left-sided limit and the right-sided limit are approaching the same value, which is -3. So it can't be B because the limit does exist. I was just confused on the difference between limits and definitions. So apologies for that. Let's move on to answer choice C. Limit as x approaches 2 does not equal g of 2. All right, I think this is the right one now because the limit as x approaches 2 is -3. We just said that because the left-sided limit equals -3 and the right-sided limit equals -3. The general limit also equals -3, but g of 2 does not equal -3. G of 2 equals -5. So that one must be our right answer since it's asking for a not equals there. Now, since this is a pretty general abstract problem, let's also run through D and E to make sure we've got our right answer. So D, g of 2 does not equal -5. That's wrong. G of 2 does equal -5. It's right there. So that one's wrong. And E, there is a vertical asymptote at x equals 2. That's not quite right. Asymptotes occur when, usually they occur when x goes down towards infinity and then goes back up on the other side. There's like a line there that it doesn't really cross, it just kind of borders it. So in this case, there is no vertical asymptote, so E is also wrong. We know that C is our right answer. Question 5, a regular derivative problem now. F of x equals 2x squared plus 16, all divided by the square root of x, and we're asked to find its derivative and then plug in 4. So, taking f of x's derivative, it looks like to start we'll need to use the quotient rule because it's a numerator and a denominator there, a fraction. So, quotient rule states if we have something in the form of a divided by b, its derivative equals a prime b minus a b prime all over b squared. So using this template and fitting it to our problem, we'll get the derivative. So f prime of x equals, so we have our fraction, and then on the top we have a prime, which is the derivative of 2x squared plus 16. So that is going to be, derivative of this, we take 2 out front, we get 4x, 2 minus 1 is 1, so the power of 1. all times b, which is square root of x, minus a, which is 2x squared plus 16, all times b prime, which is the derivative of square root of x. Derivative of square root of x, square root of x can be rewritten as x to the 1/2 power. So when we do that, it becomes clear we could just do the power rule. We take 1/2 out front, so this is 1/2 x, and then reduce it by 1. So 1/2 minus 1 is negative 1/2. So we've got the numerator now, and on the bottom it's just b squared, the denominator squared, which will just be x, square root of x squared. So we have our derivative now. I'm going to rewrite this here as something that has a square root in it and not this 1/2 power. Those are kind of hard to read and interpret and to plug in values into. So I'm going to rewrite this as, so it's 1/2 x to the negative 1/2. That'll be on the bottom. This is going to be 1 over 2 to the square root of x. So what I did there, 1/2 times, so x to the negative 1/2 is the same as 1 over x to the 1/2. And x to the 1/2 is just square root of x. And then we just put that 2 on the side there for that fraction. And that's how I got 1 over 2 to the square root of x. So now we have our derivative, and we just have to plug in 4. So f prime of 4 equals 4 times 4, which is 16, square root of 4, which is 2, minus 2 times 4 squared, so that's going to be 16 times 2, which is 32, plus 16. I'll try not to do too many steps at once. And then our last term is 1 over 2 times square root of 4, which is 2. 2 times 2 is 4, all over 4. Evaluating further, we get 16 times 2, which is 32. Let me make more room for this. 32 minus, so this will be 32 plus 16 is 48 times a fourth, all over 4. Now this is 32 minus, so 48 divided by 4 is 12, I think, all divided by 4. And now this equals 32 minus 12 is 20 divided by 4, which equals 5. That's the answer. Okay, question 6. At what points x comma y on the graph of f of x does the tangent line to f of x have a slope of negative 1/2? So that's kind of an interesting problem setup because it's usually, it's the opposite of what they usually ask you. Like normally you're asked to take the derivative of f of x and then plug in an x value into it, and then you'll get a slope coming out of that, the slope of the tangent line. But in this case, it's the opposite. You're given the slope and you're asked to find the x value and the y value. So I think the way you'd want to solve this problem is first take the derivative of f of x and then just set it equal to negative 1/2. And by doing this, you just could solve for x after that, since f of x will be the derivative of this fraction here. You just solve for x, and then that'll be your x value, or your x values in this case. So doing all that, we take the derivative of f prime of x. So that's going to be, all right, we got to do quotient rule here since we have a fraction, a quotient. So again, this is, if you have something in the form of a over b, you want to take the derivative of it. That equals a prime b minus ab prime all over b squared. So in this case, a is x and b is x minus 2. So fitting those into the template, we get, so a prime, that's the derivative of x, which is just 1. B is x minus 2 minus a, which is x, times b prime, so the derivative of x minus 2, that's just derivative of x, which is 1, minus the derivative of 2, which is 0. So we have our numerator, and our denominator is just b squared, so x minus 2 squared. So we have our derivative, and now we can just set it equal to negative 1/2 and just solve for x, and then that'll be our x values. So doing that, let's multiply things out to make this prettier. We get x minus 2 minus x all over. On the bottom we've got, so imagine if this was x minus 2 times x minus 2 squared. doing FOIL. So first is x squared. Outside is x times negative 2, negative 2x. Inside is, oh, I can't erase. I still can't erase. There you go. Inside is negative 2x, another one. And then the last, the L, is plus 4. So there we go. Now this still equals negative 1/2. We can simplify further. It looks like these two x's are going to cancel out. We get negative 2 all over x squared minus 4x plus 4 equals negative 1/2. Now we can cross multiply. So we can multiply negative 2 and 2 and set it equal to x squared minus 4x plus 4 times 1. So doing that, we get, so on the left I'm going to put negative 2 times 2, which is negative 4, equals x squared minus 4x plus 4 times 1. All right. So, oh, actually, I made a small mistake. So we forgot about this negative here. I think that's actually, this is the second take of this problem, and I think that's what I messed up on the first take. So we're going to relegate that to either the numerator or the denominator. I think the denominator makes more sense. You can make the left just a positive 4 now. All right, cool. We're all balanced out. So subtracting 4 from both sides, we get 0 equals x squared minus 4x. We can take out an x from the right side to get 0 equals x times the quantity of x minus 4. And now we can split this into two separate equations. We can split it into 0 equals x and 0 equals x minus 4. So now these are our two equations. The bottom one we can simplify to x equals 4. And that is our answer. Those are our two x values. And based on this, you can kind of detect that our answer is going to be and a 4. But let's go a little further. Let's find out those two y values. So we plug in 0 and 4 into f of x to see if we get 0 and 2. Let's double check our work. So f of 0 and f of 4 equals, all right, so this is going to give us 0 over 0 minus 2, which equals 0. Cool, that's that 0. And f of 4 equals 4 over 4 minus 2, which equals, so this is going to be 4 over 2, which equals 2. There we go. We double checked our work. We got a 2. We're chilling with answer choice C. Question 7, we're back to doing limits. So the limit as x approaches 0 of cosine x times tangent of pi of x, all divided by x. So this pi in there really messes things up, because this would be a simpler problem if this was just a tangent of x. Just like that, we could rewrite it as sine of x all over cosine of x. These two x's would cancel out. We'd just be left with sine x over x, and that's a lot easier to deal with than this big conglomerate of trig functions. But still, this is not the worst problem in the world, since I think we can just do L'Hopital's rule for this. So if we were to plug in 0 in for all these x's, we get cosine of 0, which is 1, times tangent of 0, which is also 0, and on the bottom we'd have 0. So this is 0 over 0. That's an indeterminate form, which is 0 over 0 or infinity over infinity. So since we have the indeterminate form, we can do L'Hopital's rule, where we take the derivative of both the top and the bottom separately, and our limit will stay the same. So if we take the derivative here, the top derivative is probably going to be the harder one. So this is going to invoke the product rule. So product rule, if you have something in the form of a times b, and you take its derivative, that is equal to a prime b plus ab prime. So in this case, a is cosine x and b is tangent of pi x. So plugging in those, we'll have our derivative. So we have a prime, that's the derivative of cosine x, that is negative sine x. B, that is tangent pi x. And then plus a, which is cosine x, times b prime, that's the derivative of tangent pi x. So the derivative of tangent is secant squared of pi x. Now we do need to multiply by the derivative of the inside to chain rule this. Derivative of pi x is just pi. So that is our top derivative, and on the bottom, derivative of just x is 1. So divided by 1, that don't do anything, so we're just going to keep this as that. That is our new function here. So now that we don't have a denominator, we're probably going to end up with an answer. It won't be dividing by 0 or anything once we plug in 0. So if we plug in 0 for these x's, we'll probably get our answer here. So doing that, we get negative sine of 0 is 0. This doesn't matter because we have a multiply by 0 here. So that's just going to become 0 no matter what. Plus cosine of 0 is 1 times. We have a secant here, and I don't know what the heck a secant even means. So I'm going to rewrite this as 1 over cosine squared of pi x instead. And then also put the this pi up in the top there since it's just being multiplied. So now we have that. This is going to be, so we can forget about all that. That's multiplied by 0. And also this 1 here, that's also just not going to do anything. So we're just left with this. So when we plug in 0 into it, we get pi over cosine squared of 0. Cosine of 0 is 1, and 1 squared is also 1, so we're just left with pi, which is our answer here. Question 8, we've got a double derivative this time. That's interesting. If f of x equals x sine of x, take the derivative of it twice, and then plug in pi over 2. So the first derivative of x sine of x, probably product rule here. Again, this is a very common derivative rule, the product rule here. It comes up a lot. So that's a prime b plus ab prime. Boom. So this is going to be, so f prime of x equals, so a prime derivative of x is 1, b is sine of x, plus a, which is x, times b prime, which is the derivative of sine of x, which is cosine, that's a bad s, cosine of x. Yeah, there we go. That is our first derivative. Let's make it a little nicer. Let's get rid of these multiply by 1s and also make this x cosine x. So there's our first derivative, and now the second derivative, f double prime. Is that the way that you say it, double prime? Probably not, but that's the most clear way that I can see it. So f double prime of x equals, so derivative of sine of x is cosine of x. Derivative of x cosine of x, that is another product rule. So in this case, a is x and b is cosine x. So doing all that, we get a prime, so derivative of x is 1 times b cosine of x plus a, which is x, times b prime, derivative of cosine x, that's negative sine of x. So that's that. Now we can just plug in f double prime of pi over 2 into all this and get our answer. So cosine of pi over 2 plus 1 times cosine of pi over 2 is, actually, let's just rewrite this over here. Cosine of pi over 2, excuse me, that is 0, same there, plus 0 times whatever that is, doesn't even matter because this is a multiply by 0. So that's not going to matter, that's not going to matter, and that's not going to matter. Hang on, is this equals 0? Does it actually equal 0? I actually haven't checked. Question 8 is supposed to be A. Hang on, what did I mess up here? Oh, why did I plug in oh, I messed up right here. Okay, this is pi over 2 and negative sine of pi over 2. So sine of pi over 2 is 1, so that's negative 1 there. Okay, that's how I messed up. So these still don't matter, but this is now negative pi over 2. So, okay, so the answer is actually A. So that is the answer there. So, yeah, that was just a lot of product rule and more product rule and then simplifying, and we did it. Hooray, yay, that was amazing. Question 9. Ooh, I like this question. It's like these functions within functions question. In my opinion, it's pretty satisfying to see this all worked out. I don't know why, but it's just cool to get to do these problems. So suppose that g of x equals the quantity f of x squared minus f of x squared. That's kind of confusing. Also suppose that f of 1 equals 2 and f prime of 1 equals 3. Find g prime of 1. So we need to find g of x's derivative and then plug in 1 into it. So g prime, let me make some more space, g prime of x equals the derivative of this. So it looks like it's two terms being subtracted, so we can kind of take the derivative of each of them separately. Starting with the left one, it looks like we can do power rule here, bring the 2 out front. So this is 2 of f of x. That's like the inside part, right? So then this power now is just 1 because 2 minus 1 is 1. But we do have to do chain rule. We have to multiply by the derivative of the inside, which is f of x, so we just multiply it by f prime of x. So that's that left term there. The right one now, f of x squared. This is going to be f prime of x squared. And then another chain rule here. We have to multiply by the derivative of the inside. The inside is x squared, so we just multiply by its derivative, which is 2x. So that is our derivative. Now doing g prime of 1, plugging in 1 for all these x's, we get 2 of 2 times f of 1 times, let me actually make these all parentheses, that's clearer, I think, times f prime of 1 minus f prime of 1 squared, which is just 1, times 2 times 1. So there we go. Simplifying, we get 2 times f of 1 is 2, f prime of 1 is 3, minus f prime of 1 is 3 times 2. Simplifying, we get 4 times 3 is 12, minus 6 equals 6. D. Question 10, another derivative one, just phrased a little differently using a dy over dx instead of like an f prime of x or something, but in the context of this problem, they mean the same thing. So derivative of cosine cubed of the quantity of 1 minus 2x, taking its derivative will give us our answer. So I think the first thing we need to do, we can rewrite this as, so dy over dx equals cosine of 1 minus 2x, all of that cubed. Right, rewriting it like this is exactly the same thing. I don't know why, I think they put the cubed there because if they put it here, it kind of looks like it's affecting the inside here and not, the whole thing, which it is. So by rewriting it the way I have here, it becomes clearer that the cubed is acting upon the whole. And we can see that we could do the power rule. We can bring that 3 out front and then reduce it by 1 to do the derivative. So this equals 3 times, this will be cosine of 1 minus 2x squared, and then it times, then we have to do chain rule, we have to multiply by the derivative of the inside. We have to multiply by the derivative of cosine of 1 minus 2x. So this is going to be sine, or negative sine of 1 minus 2x times, we have to do another chain rule. We have to multiply by the inside of the sign there, the 1 minus 2x, and that is going to be negative 2. So that's our derivative. Now it looks like it wants us to crunch it down into something smaller. So let's see what we can do here. This 3 and this negative 2 can combine to make negative 6 cosine squared of 1 minus 2x times negative sine of 1 minus 2x. This negative can be moved out front to make positive 6 cosine squared of 1 minus 2x times sine of 1 minus 2x. What else can we do here? Oh, no, that's our answer. It's D. It just swapped the sine and the cosine. We have our answer. Question 11. For any time t greater than 0, the position of a particle is given by s of t, the position function. What is the acceleration of the particle at the point where the velocity is first equal to 0? All right, that's three different derivatives of our position function. We've got the original, which is this, the position function. We've got the second derivative, the acceleration, and the first derivative, the velocity. We're probably going to have to do two derivatives here to get our answer. So how do we actually get that, though? What's our path to the answer? Well, it looks like the first thing we have to do is take the derivative of s of t to get our velocity function, and then we can set that velocity function equal to 0 to get that point where the velocity equals 0, to get that time when the velocity equals 0. So doing that, s of t, or s prime of t, which equals v of t, the velocity function, that equals, so derivative of sine t is cosine t, plus or minus the derivative of cosine t, which is negative sine t, so that's going to be plus sine t. That is our velocity function. What we can do is we can set that equal to 0, and cosine t plus sine t, and solve for t. And then that'll be the time that we need to find the acceleration at. Unfortunately for us, due to the nature of trig functions, this is probably going to have an infinite number of solutions, since you know how sine waves look and cosine waves. For some outputs, there's an infinite number of inputs. And it looks like that's going to be the case here. We're probably going to have an infinite number of t values that will satisfy this equation. Now, fortunately for us, it's just asking for the first one, the one that is essentially lowest, the smallest one that is still greater than 0. So we can go ahead and find that by using our unit circle table, which I don't really know the full version of. Like, off the top of my head, I don't know each value. Like, I couldn't, graph out the full table and all those values that you might know, but I don't know that. So I think what the answer is going to be here is some form of pi over 4. So on the unit circle, unit circle like that, that is this line here where there's a 45-degree angle right there. Sine of pi over 4 is root 2 over 2, and cosine of pi over 4 is also root 2 over 2. So I think it's going to be either pi over 4 or 3 pi over 4 or 5 pi over 4 or 7 pi over 4, but I think it's going to be one of these two. So we can just go ahead and test both of those and see which one it is. So testing pi over 4, 0 equals cosine of pi over 4 plus sine of pi over 4. This is going to give us 0 equals, let's see, cosine of pi over 4 is, we just said it's root 2 over 2, plus sine of pi over 4 is also root 2 over 2. This doesn't check out. This is going to evaluate to 2 root 2, or just root 2, actually. This is going to be just root 2. That doesn't work. Now our answer is probably going to be 3 pi over 4, but let's double check. Let's do 0 equals cosine pi over 4 plus, or 3 pi over 4 plus sine of 3 pi over 4. Let's see what we get. So cosine of 3 pi over 4, if you go all the way around the unit circle like that, that is going to be negative root 2 over 2. And sine of 3 pi over 4 is going to be positive root 2 over 2. So yes, we know we did things right. This checks out. We know that our lowest t value is 3 pi over 4. So knowing that, we can plug that into the acceleration function, and we'll get our answer. Our acceleration function is just v prime of t. So doing that, the second derivative of our original s of t is going to be, let's see, derivative of cosine of t is negative sine of t, and derivative of sine of t is cosine of t. So we've got that now. Now just plugging in 3 pi over 4 in for these t's, we get negative sine of 3 pi over 4 plus cosine of 3 pi over 4. Sine of 3 pi over 4, we just said is root 2 over 2. So this is going to be negative root 2 over 2, actually, because of the negative here. Plus cosine of 3 pi over 4, which is negative. Actually, it's going to be negative root 2 over 2, because cosine of 3 pi over 4 is negative. I don't know why it took so long to say that. So negative root 2 over 2 minus root 2 over 2, that's just going to be equal to negative root 2, and that's our answer. So yeah, just a bunch of unit circle stuff, which I don't really like, to be honest. Question 12. Another derivative question. The slope of the line tangent of the curve described by this at this point is what? So derivative question. I wonder what form of differentiation we should use for this problem. I wonder what convenient form of derivatives would work for this problem. Oh, yes, you're exactly right. The answer is implicit differentiation. That's what we should use for this problem, especially because A, we're given a value to plug in that's a form of a point, not just an x value. It gives us an x and a y value. And B, the thing we're trying to derive is super yucky. It has a bunch of nested y's that would be very annoying to get back in the form of y equals. So that would be hell. So instead, we're going to do implicit differentiation. And how this works is if you basically just take a derivative of every term, all by themselves like normal. And if you ever take the derivative of a y, you multiply it by dy over dx. And at the end, you plug in 2 for x and 1 for y. You'll be left with dy over dx, and you just solve for it, and that'll be your variable. So doing all that, let's take the derivative of this now. First derivative of this first term, y cubed x. Looks like we're going to have to do product rule for that. So that is a times b. Derivative of that equals a prime b plus ab prime. I'm running out of steam. My throat is raw. But anyways, so doing this first one now is a prime, which is the derivative of y cubed, that's going to be 3y squared, and we just took the derivative of y cubed, which had a y in it, so we're going to multiply this by dy over dx, and just save it for later. We're going to keep it right there. So now b is x, plus a is y cubed, times b prime, derivative of x, which is just 1. We took the derivative of an x, which isn't a y, so we don't have a dy over dx there. And then plus, so now we're moving on to this term, which, we have to do product rule again. So in this case, a is y squared and b is x squared. So plus a prime, which is derivative of y squared, that's 2y. Got to multiply it by dy over dx, since we just took the derivative of a y, times b, which is x squared, plus a, which is y squared, times b prime, which is the derivative of x squared, that is 2x. That all equals derivative of 6, which is 0. So there we go. We've done our implicit differentiation. Now we can go ahead and plug in 2 for x and 1 for y and get a solution that only has dy over dx in it. So let's do that now. This is going to be 3 times 1 squared dy over dx times 2 plus 1 cubed times 1 plus 2 times 1 dy over dx. That is a crappy y. Times 2 squared plus y squared. So 1 squared 2 times 2 times 2 equals 0. Oh my god, we're so close, I can feel it. All right, one more pass. We have 3 times dy over dx times 2. Let's actually merge that. Let's make that a 6. Plus 1 cubed is 1. 1 times 1 is 1, so plus 1. Plus 2 times 4, which is 8 dy over dx plus 1 times 4, which is 4, equals 0. Merging everything, we'll get 14 dy over dx plus 5 equals 0. 14 dy over dx equals negative 5. And dividing both sides by 14, we get dy of dx equals negative 5/14. There we go. Full exam done.